The universe is an endless expanse of mystery, an infinite tapestry woven with threads of cosmic wonder that stretches far beyond human comprehension, where the very fabric of space and time bends under the influence of forces so powerful that they defy our understanding. And yet, within this vast and seemingly chaotic abyss, there exists an intricate order, a dance of celestial bodies governed by laws so precise that they dictate the movement of entire galaxies with breathtaking synchronicity. And at the heart of this grand cosmic stage lies a burning question that has captivated the minds of scientists, philosophers, and dreamers alike for centuries. A question that whispers through the silent void of space, urging us to look deeper, to push the boundaries of our knowledge, to seek answers hidden in the dark matter that makes up most of our universe yet remains elusive. An enigma whose existence can only be inferred through gravitational effects, leading us to ponder whether we are on the brink of unraveling the greatest secrets of existence, or if we are merely scratching the surface of a reality more complex than we ever imagined, a reality where black holes lurk like cosmic predators, warping time and swallowing light, where neutron stars, the remnants of once massive suns, spin at unfathomable speeds, emitting beams of radiation so intense that they can be detected from across the galaxy, where the birth and death of stars create elements that form the very building blocks of life itself, binding us to the cosmos in ways that transcend our earthly limitations. A reality where exoplanets orbit distant stars, some within habitable zones that may harbor life, raising the possibility that we are not alone, that somewhere in the uncharted depths of the universe, intelligent beings may be looking back at us, wondering the same thing, searching for the same answers. For every discovery we make opens new doors, challenges old assumptions, and forces us to confront the unknown with a mix of awe and trepidation. As we attempt to decipher the cosmic code written in the background radiation left over from the Big Bang, the faint echoes of a beginning so violent, yet so precise, that it set the stage for everything that followed, from the formation of the first atoms to the emergence of galaxies, stars, and ultimately, us, fragile beings standing on a tiny rock, hurtling through space at incomprehensible speeds, clinging to the belief that through the power of curiosity and the relentless pursuit of knowledge, we might one day unlock the ultimate truth of our existence. For the deeper we look into the abyss, the more we realize that the universe is not just out there, but within us, woven into the very molecules of our being, whispering secrets that only those who dare to question, to dream, to explore, may one day uncover. For in the endless darkness of space, we find not emptiness, but infinite possibility, a cosmic riddle waiting to be solved, a story written in the stars that will continue long after we are gone, an unbroken chain of mysteries that stretch across time itself, inviting us to take one more step, to push one more boundary, to reach beyond what we know and embrace the unknown. For in that pursuit, in that endless quest for understanding, lies the true essence of what it means to be human, to look up at the night sky and wonder not just what is out there, but why. And in that moment, as we stare into the cosmic abyss, we realize that the universe is not separate from us, but a part of us, a reflection of our endless curiosity, a mirror of our own infinite potential. And perhaps, just perhaps, the answers we seek have been within us all along, waiting for the right moment to reveal themselves, hidden in the light of distant stars, in the silent whispers of the cosmic wind, in the vast, unfathomable beauty of a universe that continues to expand, not just in space but in our understanding, drawing us ever closer to the truth that we are, in every sense, children of the stars, bound by the same cosmic dust that forged galaxies and dreams alike. And as we venture further into the unknown, chasing the mysteries that lie beyond the edge of human perception, we are not merely observers but participants in a grand cosmic story. A story that began billions of years ago and will continue long after we are gone. A story written in the language of physics, chemistry, and time itself. Unfolding in a symphony of cosmic events so vast and intricate that they defy imagination, yet within them lies the essence of all that we are and all that we may one day become. From the moment early humans gazed up at the night sky, they were captivated by the celestial sphere, seeking patterns, meaning, and order within the vast cosmic expanse. This curiosity laid the foundation for humanity's evolving understanding of the universe, a journey that began with myth and speculation and has since led to scientific revolutions, technological advancements, and a profound awareness of our place in the cosmos. The development of cosmology, from ancient civilizations to modern astrophysics, has been shaped by a series of key discoveries and milestones, each contributing to our comprehension of the observable universe and the underlying principles governing its structure and evolution. The earliest recorded astronomical observations date back to ancient Mesopotamia, where Sumerians and Babylonians meticulously charted the motions of celestial bodies, believing them to be divine messengers influencing earthly events. Their sophisticated star catalogs and predictive models of planetary movements laid the groundwork for later astronomical advancements. The Egyptians, too, relied on celestial observations, aligning their monumental structures, such as the pyramids, with key astronomical markers. Across the globe, ancient Chinese astronomers recorded solar and lunar eclipses, while the Maya developed intricate calendrical systems based on celestial cycles. These early civilizations, though limited in their understanding of physical laws, demonstrated a remarkable ability to recognize patterns and predict cosmic events, setting the stage for systematic astronomical inquiry. The philosophical contributions of ancient Greece marked a significant shift toward rational explanations of celestial phenomena. Thales of Miletus, one of the first Greek philosophers, proposed that the universe followed natural laws rather than being solely governed by the whims of deities. Pythagoras suggested that mathematical principles underpin the cosmos, a notion that would later prove fundamental to scientific inquiry. The geocentric model, championed by Aristotle and later refined by Ptolemy in the 2nd century CE, posited that Earth was the center of the universe, with celestial bodies moving in perfect crystalline spheres around it. Though incorrect, the Ptolemaic system dominated astronomical thought for over a millennium, largely due to its alignment with religious and philosophical doctrines. The paradigm began to shift during the Renaissance, as observational evidence challenged long-held beliefs. Nicolaus Copernicus, in his seminal work De Revolutionibus Orbium Coelestium 1543, proposed the heliocentric model, asserting that the Sunday, not Earth, was the center of the solar system. Though controversial, this idea gained traction as subsequent astronomers built upon it. Tycho Brahe's meticulous naked-eye observations provided crucial data, which his assistant Johannes Kepler used to formulate the laws of planetary motion, revealing that planets moved in elliptical rather than circular orbits. Galileo Galilei, utilizing one of the earliest telescopes, made groundbreaking discoveries, including the moons of Jupiter, the phases of Venus, and the rugged surface of the moon, findings that directly contradicted the Aristotelian view of a perfect celestial realm. The next major breakthrough came with Isaac Newton's Principia Mathematica, 1687, in which he formulated the laws of motion and universal gravitation. Newton's work provided a comprehensive framework for understanding celestial mechanics, explaining how planets remained in orbit and offering a predictive tool that would guide astronomy for centuries. His ideas reinforced the notion that the universe operated according to precise mathematical principles, a concept that would inspire future scientific revolutions. The 19th and 20th centuries ushered in a new era of cosmology, driven by advancements in observational technology and theoretical physics. The development of spectroscopy allowed astronomers to analyze the composition of stars, revealing that they were made of the same elements found on Earth, further cementing the idea of a unified cosmos. In 1915, Albert Einstein introduced his general theory of relativity, fundamentally altering our understanding of space, time, and gravity. His equations predicted that massive objects could warp the fabric of space-time, leading to phenomena such as black holes and gravitational lensing. Shortly thereafter, Edwin Hubble's observations of distant galaxies provided empirical evidence that the universe was expanding, a discovery that laid the foundation for the Big Bang Theory. The concept of an expanding universe challenged earlier steady-state models, suggesting that the cosmos had a finite beginning. In 1964, the discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson provided compelling evidence for the Big Bang, confirming that the universe had emerged from an extremely hot and dense state approximately 13.8 billion years ago. This realization revolutionized cosmology, prompting new questions about the nature of dark matter, dark energy, and the fundamental forces shaping the cosmos. Parallel to these theoretical advancements, space exploration provided direct access to the universe beyond Earth. The launch of Sputnik, won by the Soviet Union in 1957, marked the beginning of the space age, demonstrating humanity's ability to send objects beyond the confines of our planet. The Apollo program, culminating in the moon landing of 1969, showcased the potential for human space travel and deepened our understanding of celestial bodies. Robotic missions to the outer planets, such as the Voyager probes, revealed the complexity of our solar system, while space telescopes like Hubble expanded our view of the distant universe, capturing images of galaxies billions of light years away. The modern era of cosmology is defined by an ongoing quest to understand the most elusive aspects of the universe. The discovery of exoplanets, planets orbiting stars outside our solar system has fueled speculation about the possibility of extraterrestrial life. The detection of gravitational waves in 2015 confirmed one of Einstein's last untested predictions, offering a new way to observe cosmic events such as black hole mergers. The James Webb Space Telescope, launched in 2021, has begun to peer deeper into the universe than ever before, shedding light on the earliest galaxies and the formation of planetary systems. A central concept in contemporary cosmology is the observable universe, the portion of the cosmos that we can see, limited by the speed of light and the finite age of the universe. Since light takes time to travel, observing distant galaxies allows us to look back in time, witnessing the universe as it was billions of years ago. However, the observable universe is merely a fraction of the total cosmos, which may extend far beyond what we can detect, potentially even being infinite. The idea of a multiverse, multiple, possibly infinite universes existing beyond our own, remains a speculative but intriguing possibility. As our understanding of the universe continues to evolve, we are left with profound questions. What is the true nature of dark matter and dark energy, which together make up the majority of the cosmos yet remain undetectable except through their gravitational effects? Are we alone, or is life a common phenomenon in the vast expanse of space? Will humanity one day become an interstellar civilization, exploring beyond the boundaries of our solar system? The pursuit of these answers reflects the essence of scientific exploration, the relentless drive to uncover the unknown, to challenge assumptions, and to push beyond the limits of human understanding. Humanity's journey from myth to science, from superstition to empirical inquiry, has been a testament to the power of curiosity and intellect. Each discovery, from Copernicus to Hubble, from Newton to Einstein, has reshaped our perception of the cosmos, revealing a universe that is not static but dynamic, not finite but ever-expanding. As we continue to explore the frontiers of space and physics, one thing remains certain: the story of the universe is far from complete, and the greatest discoveries may still lie ahead. The universe is vast beyond comprehension, an endless expanse of galaxies, stars, and cosmic mysteries, stretching across distances so immense that the human mind struggles to grasp them. It is both breathtakingly beautiful and terrifyingly indifferent, a realm where unimaginable forces shape existence on scales that dwarf our own. And yet, despite our insignificance in this grand cosmic stage, the universe calls to us, igniting a fire of curiosity deep within the human spirit. We look up at the night sky, and something stirs in an instinctive, almost primal desire to understand, to explore, to know what lies beyond. This emotional pull, this sense of wonder mixed with fear, has been a defining part of our existence for millennia. Why should we care about the universe? Because it is more than just a collection of distant celestial bodies. It is a mirror that reflects our own nature, our deepest questions, and our relentless pursuit of meaning. At the heart of this emotional connection is the feeling of wonder and awe that transcends mere knowledge. When we gaze at the Milky Way on a clear night, we are seeing a river of stars so vast that it takes light tens of thousands of years to travel across it. Each of those stars may have planets, and on some of those planets, life may exist. Looking back at us, with the same sense of curiosity. The idea that we are part of something so incomprehensibly large, so intricate and bound by natural laws that seem almost designed to create life and consciousness, is both humbling and exhilarating. The fact that we can even comprehend these ideas, that we have developed the tools to peer into the distant past and decode the birth of the cosmos, is nothing short of a miracle. Every new discovery, whether it's an exoplanet in a habitable zone, a new signal from deep space, or the detection of gravitational waves, expands our sense of possibility. It reminds us that we are still explorers, that the human story is not confined to the Earth, but is part of something much greater. But with wonder comes fear, the fear of the unknown, of insignificance, of what we might find if we keep searching. Space is not a welcoming place. It is a void of silence, where distances are so vast that even the fastest spacecraft we can build would take tens of thousands of years to reach the nearest star. It is a realm where stars collapse into black holes so powerful that not even light can escape, where entire galaxies collide in cosmic dances spanning millions of years, where planets are torn apart by gravitational forces beyond our comprehension. There is something deeply unsettling about knowing that, in the grand scale of the universe, we are nothing more than a flicker of light, brief, fragile, and easily extinguished. If Earth were to disappear tomorrow, the universe would continue, indifferent to our fate. And yet, this very fear, this confrontation with the vast and uncaring cosmos, gives our existence weight. The knowledge that we are small does not diminish us. It makes our moments, our struggles, our triumphs, all the more meaningful. In a universe that does not grant us inherent significance, we create our own. This duality, wonder and fear, fuels a deep existential curiosity. Why are we here? Is there a purpose to our existence? Or are we merely an accident of physics and chemistry, a statistical improbability in an otherwise indifferent universe? These are questions that have driven philosophy, religion, and science for thousands of years. Some look to the stars for answers, hoping to find other intelligent life that might confirm that we are not alone, that our existence is part of a larger pattern. Others see the lack of contact with extraterrestrial civilizations, the so-called Fermi paradox, as evidence that we may be utterly alone, the first and only sentient beings to emerge in this vast expanse. The thought is both exhilarating and terrifying. If we are alone, then the responsibility of carrying forward the light of consciousness falls solely upon us. Every action we take, every step forward in science, art, and exploration is an act of defiance against the darkness, a declaration that we are here, that we matter. And yet, even as we contemplate our place in the cosmos, the universe remains deeply personal. Each of us, in our own way, has felt the pull of the infinite. For some, it comes in childhood, lying in the grass and staring at the stars, wondering what it would be like to travel among them. For others, it is the realization that the atoms in our bodies were forged in the hearts of ancient stars, that we are literally made of stardust. This connection between the vast and the intimate, between the infinite and the personal, is what makes the cosmos so profoundly moving. It is a reminder that, despite the cold equations of physics, there is beauty, there is meaning, and there is a story being written, one that we are a part of. Space exploration, then, is not just about science. It is about answering this deep emotional call. Every mission to Mars, every telescope pointed at the edge of the universe, is an act of curiosity, of hope, of seeking something greater than ourselves. When humans first set foot on the moon, the world watched not just because it was a technological achievement, but because it was a moment that transcended politics, borders, and individual concerns. It was a testament to what humanity can achieve when we dare to dream. And as we now look toward Mars, toward the possibility of interstellar travel, we are not merely chasing scientific goals, we are following an ancient instinct, and the same one that led our ancestors to sail across unknown oceans and chart unclaimed lands. It is the same force that pushes artists to create, that drives philosophers to question, that compels us to look beyond our immediate existence and imagine what lies beyond. But there is also a quieter, more reflective aspect to this emotional connection. The universe teaches us patience. It operates on timescales so vast that human lifetimes are mere blinks in comparison. Stars are born, live, and die over billions of years. Galaxies take eons to collide and merge. The very fabric of the universe stretches over incomprehensible distances. In this grand timeline, our struggles, our anxieties, our daily concerns seem minuscule. This perspective can be overwhelming, but it can also be liberating. It reminds us that life is fleeting and that we should embrace the wonder of existence while we can. It teaches us to be humble, to appreciate the beauty of a single moment, to marvel at the fact that we are here at all. And yet, despite all we have learned, there is still so much we do not know. What lies beyond the observable universe? What is the true nature of dark matter and dark energy? Could we one day unlock the secrets of time itself? The unknown is both terrifying and intoxicating, a vast ocean stretching endlessly before us, daring us to set sail. Some may find comfort in certainty, in fixed answers and defined boundaries. But for those who embrace the mystery, who lean into the unknown rather than shrink from it, the universe offers something more profound: a lifelong journey of discovery, an endless unfolding of truths yet to be revealed. Ultimately, we care about the universe because it reflects our deepest desires to explore, to understand, to find meaning. It is a story without end, a mystery without a final answer, an adventure that spans both time and space. Whether we seek solace in its vastness, inspiration in its beauty, or meaning in its mysteries, the cosmos remains an inseparable part of who we are. To look up at the stars is to connect with something ancient and universal, to join in a conversation that has been ongoing since the dawn of humanity. And as long as we continue to ask questions, to push beyond our limitations, and to dream of what lies beyond, we will never truly be lost in the vastness of space. Instead, we will find ourselves over and over again in the reflection of the infinite. When you look up at the night sky, what do you see? Is it merely a vast emptiness dotted with distant stars? Or do you sense something deeper, a mystery so profound that it defies our ability to fully comprehend it? The universe is not just a collection of celestial objects scattered across an endless void. It is a living puzzle, a story unfolding across billions of years, a riddle written in the language of light, gravity, and time. And the most intriguing part of it all? We are right in the middle of it, observers and participants in an ongoing cosmic narrative, struggling to understand our own role in this grand design. But what if the questions we ask about the universe are not just about distant galaxies or the birth of stars, but about ourselves? What if solving the mysteries of the cosmos helps us unlock the deepest truths about existence, consciousness, and the fundamental nature of reality? Consider the fact that the atoms in your body, very particle that makes up your skin, bones, and mind, were forged in the hearts of ancient stars that lived and died billions of years ago. This is not a poetic metaphor, but a scientific reality. You are made of stardust, the very same material that composes the universe itself. Does this change how you perceive your place in the cosmos? Does it make you feel more connected to the universe? Or does it make you feel even smaller in the face of its unimaginable scale? The more we learn, the more we realize how deeply intertwined we are with the fabric of existence itself. And yet, for all our discoveries, we are still left with some of the most unsettling and profound questions. What is the true nature of reality? Are we alone in the universe? Is our understanding of time and space even remotely accurate? Or are there aspects of existence that we have not yet begun to grasp? One of the greatest challenges of modern cosmology is confronting the unknown. For centuries, we believed that the observable universe contained everything that existed. But now, we know that we are only seeing a tiny fraction of what's out there. Dark matter and dark energy, two of the most perplexing concepts in physics together, make up approximately 95% of the total mass energy of the universe. Yet we have no idea what they actually are. We know dark matter exists because of its gravitational influence, but we cannot see it or interact with it in any meaningful way. Similarly, dark energy is thought to be responsible for the accelerating expansion of the universe, but its true nature remains a mystery. How does it feel to know that everything we have ever studied, every planet, every star, every galaxy, accounts for less than 5% of what actually exists? Does that make you excited, knowing that there is so much left to discover? Or does it make you uneasy, knowing that the majority of the universe remains invisible and unexplained? And then there is the question of extraterrestrial life. If the universe is as vast as we believe it to be, with billions of galaxies, each containing billions of stars and even more planets, then it seems almost inevitable that life must exist somewhere else. Yet, despite decades of searching, we have found no definitive proof. This paradox, the contradiction between the high probability of alien life and the complete lack of evidence, is one of the greatest scientific mysteries of our time. What if we are truly alone, the only sentient beings in an otherwise lifeless universe? What would that mean for our purpose, for our responsibility as the sole carriers of consciousness? Or what if we are not alone and intelligent life exists elsewhere? Would we be ready for such a discovery? How would it change the way we see ourselves, our religions, our cultures, and our place in the grand cosmic order? Every breakthrough in space exploration brings us closer to answering these fundamental questions. The James Webb Space Telescope is currently peering into the deepest reaches of space, analyzing the atmospheres of distant exoplanets in search of biosignature chemical markers that could indicate the presence of life. Future missions to Mars aim to determine whether microbial life ever existed beneath its surface. Scientists are even developing new ways to listen for alien signals, hoping to intercept messages from other civilizations. But what happens if one day we wake up to the news that we are not alone? Would it unite humanity, forcing us to see ourselves as one species instead of separate nations? Or would it create new divisions, new fears, new conflicts? These are not just hypothetical questions. They are real possibilities that could unfold within our lifetime. But the mysteries of the universe are not limited to the search for life. Time itself is a concept that remains largely misunderstood. According to Einstein's theory of relativity, time is not an absolute constant. It stretches and contracts depending on gravity and velocity. This means that in different parts of the universe, time moves at different rates. In the intense gravitational field of a black hole, time slows down to such an extent that an observer falling into one would appear to freeze from an outside perspective. If we could harness these effects, could time travel one day be possible? Could we use black holes or wormholes as shortcuts through space-time, allowing us to reach distant galaxies in a matter of moments? And if so, what would that mean for our understanding of cause and effect, of free will, of reality itself? Even the concept of the universe having a beginning challenges our most basic understanding of existence. The Big Bang Theory tells us that everything, the entirety of space and time, emerged from a single, infinitely small point. But what came before that? Was there ever a before? Or does the question itself not make sense in the context of a universe where time itself was created in that moment? And if our universe had a beginning, will it also have an end? Will it continue expanding forever, growing colder and more desolate as stars burn out one by one? Or will it eventually collapse in on itself, triggering another cosmic rebirth? Some scientists believe in the possibility of a multiverse, an infinite number of universes existing simultaneously, each with its own set of physical laws. If that is true, then everything we know, everything we have ever experienced, may be just one of countless realities. What does that mean for our sense of self? Is our consciousness limited to this one reality? Or could there be versions of us existing in other parallel universes, living out different possibilities? The beauty of these questions is that they are not just the domain of scientists and philosophers. They belong to all of us. They challenge us to think beyond our daily routines, to step outside of our immediate concerns, and to engage with something much larger than ourselves. The universe invites us to wonder, to dream, and to imagine possibilities beyond what we currently understand. It is a call to exploration, not just of the cosmos, but of our own minds and beliefs. How do you personally grapple with these vast mysteries? Do they excite you, make you feel small, or fill you with a sense of purpose? Have you ever had a moment where you truly felt connected to the universe, perhaps standing beneath a sky full of stars, or watching a sunset and realizing that the same sun has risen and set for billions of years? The discussion about the universe is not just about finding answers. It is about engaging with the unknown in a way that expands our perspective. The more we learn, the more questions arise. And that is a beautiful thing. It means that we are still at the beginning of a great cosmic journey, one that will continue long after we are gone. So let's talk about it. What do you believe about the mysteries of the cosmos? What discoveries do you think will change our understanding of reality? What questions keep you awake at night as you stare into the infinite expanse of space? The universe is speaking to us in the language of light and gravity, in the silent whispers of distant stars and the faint echoes of the Big Bang. All we have to do is listen, and perhaps, in doing so, we will not only discover the secrets of the cosmos, but also uncover something profound about ourselves. The cosmos is an endless expanse, a boundless ocean of light and darkness, stretching far beyond the limits of human perception. It is a place where time itself bends under the weight of gravity, where entire galaxies spin in an intricate cosmic dance, and where the birth and death of stars unfold like celestial poetry across the backdrop of eternity. To stand beneath the night sky is to feel the presence of something vast and unknowable, an overwhelming sense of awe in the face of infinity. It is in this void that some of the greatest mysteries of existence hide, waiting to be unraveled, whispering their secrets through the silent language of light, gravity, and time. Imagine drifting through intergalactic space, far beyond the familiar spiral arms of the Milky Way, where the faint glow of distant galaxies flickers like embers, scattered across an endless void. The universe here is quiet, almost eerily so. There is no sound, no air to carry vibrations, only the steady hum of radiation and the slow, deliberate motion of celestial bodies governed by unseen forces. A lone galaxy, hundreds of thousands of light years across, spirals in the darkness, its glowing core a cauldron of immense energy, where millions of stars are born and die in violent explosions that shape the very structure of space. Swirling clouds of gas stretch across the galactic arms, illuminated by the radiation of newborn suns, their hydrogen-rich tendrils forging the elements that will one day become planets, and perhaps, life. Beyond the luminous heart of galaxies lies the great abyss of intergalactic space, a vast and nearly empty void where light itself seems reluctant to travel. These cosmic voids, some spanning hundreds of millions of light years, are among the most enigmatic regions of the universe, places where matter is so scarce that galaxies seem like distant islands adrift in an endless sea. The silence of these regions is profound, an emptiness so complete that it challenges our understanding of existence itself. What forces created these voids? Are they merely the absence of galaxies? Or could they harbor secrets yet to be discovered, hidden realms beyond the reach of our instruments? Yet, even in these seemingly empty stretches of space, there is something invisible, something exerting a force that shapes the cosmos in ways we do not fully understand. This is dark matter, the unseen scaffolding of the universe. Though we cannot see it, we know it is there because of its gravitational influence on galaxies, bending light and warping space-time itself. Without it, galaxies would not hold together. Their stars would fly apart, scattered into the void. But what is dark matter? Is it composed of undiscovered particles, or is it something even more exotic? A fundamental aspect of reality that we have yet to comprehend. And then, even more perplexing, there is dark energy, the mysterious force accelerating the expansion of the universe. Unlike anything we have ever encountered, dark energy pushes against gravity itself, driving galaxies apart at an ever-increasing rate. If it continues unchecked, the universe may one day become a cold, empty expanse where all stars have burned out, where galaxies drift so far apart that their light will never again reach one another, leaving a universe of infinite loneliness. Or could dark energy be something else entirely, a sign that our understanding of physics is incomplete? Is it possible that we are missing a fundamental piece of the cosmic puzzle, something that will reshape our perception of existence itself? The quest to answer these questions has been taken up by some of the greatest minds in cosmology, those who have dedicated their lives to understanding the nature of the universe. Albert Einstein, whose general theory of relativity revolutionized our understanding of space and time, once believed in a static universe and introduced the infamous cosmological constant to balance his equations, only to later discard it as his greatest mistake. Ironically, we now know that a similar force does exist: dark energy, which drives the expansion of space. Edwin Hubble, through meticulous observation, proved that the universe was not static but expanding, leading to the birth of the Big Bang Theory and fundamentally altering our view of cosmic history. Stephen Hawking, with his groundbreaking work on black holes, revealed that these terrifying cosmic giants might not be as inescapable as once thought, that they might slowly evaporate over time through a process now known as Hawking radiation. Today, modern astrophysicists and cosmologists continue to push the boundaries of our understanding. The James Webb Space Telescope peers into the early universe, capturing light from galaxies formed billions of years ago, revealing the origins of structure itself. The hunt for dark matter continues in underground laboratories, where scientists hope to detect the faintest interactions of unknown particles that could finally explain its nature. The search for life on exoplanets grows ever more promising as we analyze the atmospheres of distant worlds, searching for the chemical fingerprints of biology. Each new discovery brings more questions, more mysteries, more reasons to explore. And yet, despite all we have learned, the universe remains a place of profound mystery. We do not know what lies beyond the observable horizon, beyond the limits of the cosmic microwave background, the faint afterglow of the Big Bang that marks the edge of what we can see. Could the universe be infinite? Could it be just one of many in an endless multiverse, each with its own laws of physics, its own history, its own version of reality? The implications are staggering. If there are infinite universes, then somewhere, in some distant cosmic realm, another version of you might exist, living a life just slightly different from your own. Or perhaps, in some universes, the laws of physics are so different that life as we know it is impossible, that reality itself takes on forms beyond our comprehension. The universe invites us to wonder, to question, to dream of what might be. It is a place of endless beauty and unimaginable terror, where stars are born in clouds of fire and collapse into darkness, where time can slow to a crawl or stretch into infinity, where entire galaxies are torn apart by unseen forces. It is a place where we search for meaning, for connection, for answers to the greatest questions ever asked. Are we alone? What is the fate of the cosmos? What lies beyond the limits of what we can see? To explore the universe is to explore ourselves. It is to confront our deepest fears and embrace our greatest hopes. It is to recognize that we are, for all our smallness, part of something grand, something ancient, something eternal. And though we may never have all the answers, the pursuit itself, the journey of discovery, is what defines us. The universe is not just out there, in the distant reaches of space. It is within us, woven into the very fabric of our being. It is in the atoms of our bodies, in the curiosity that drives us to ask questions, in the relentless desire to push beyond the known. And so, we continue to look up, to wonder, to reach for the stars, not because we expect to find all the answers, but because the act of searching itself is what makes us who we are. In the silence of the cosmic void, we listen for echoes of the past, for signals of the unknown, for the whispers of the universe telling us that the greatest mysteries are still waiting to be uncovered. The universe stretches far beyond the limits of human perception, an ever-expanding frontier of knowledge that seems to recede the closer we think we come to grasping it. Every time we uncover a new piece of the cosmic puzzle, we find ourselves facing deeper questions, more profound mysteries, and paradoxes that suggest we may never truly reach the edge of understanding. What if the nature of the cosmos is such that every answer only generates more uncertainty? What if, by seeking the limits of reality, we only reveal how limitless it truly is? The greatest conflict in cosmology is not between competing theories or scientific camps, but between our desire for absolute knowledge and the fundamental structure of the universe itself, which may be designed to forever elude complete comprehension. One of the first indications that the universe defies simple answers is the problem of the horizon. How can the observable universe appear so uniform in temperature when, by all known physical laws, regions separated by billions of light years should never have been able to exchange information or energy? The cosmic microwave background radiation, a relic from the Big Bang, is nearly identical in every direction, as if the entire cosmos had somehow communicated with itself in the earliest moments of existence. This contradiction led to the theory of cosmic inflation, a brief period of exponential expansion that stretched space faster than the speed of light itself. But if inflation explains this paradox, it also raises new ones. What caused it? And could it still be happening? If the inflationary process is eternal, generating new universes endlessly, then our observable universe may be just one bubble in an infinite multiverse, making the concept of a final edge of reality meaningless. Could we ever confirm or disprove such a vast idea, or will the truth always remain just out of reach? Then there is the paradox of dark matter and dark energy together, comprising 95% of the universe's mass energy, yet completely undetectable, except through indirect effects. Our observations of galaxies suggest that dark matter is necessary to explain their rotation, yet despite decades of searching, we have failed to directly observe a single dark matter particle. Could it be that we are fundamentally misinterpreting gravity itself? Alternative theories, such as modified Newtonian dynamics, attempt to explain galactic motion without invoking an unseen substance, but no single model has been able to fully reconcile the discrepancies. Dark energy presents an even greater enigma, as it appears to be accelerating the expansion of the universe in defiance of everything we thought we knew about gravity. If we cannot see, touch, or measure most of what makes up the cosmos, how can we claim to understand it? At the very heart of modern physics lies another profound contradiction: the apparent incompatibility between general relativity and quantum mechanics. Einstein's equations describe gravity as the curvature of space-time, a smooth and continuous fabric, while quantum mechanics tells us that at the smallest scales, reality is chaotic and probabilistic, filled with virtual particles flickering in and out of existence. When we attempt to apply general relativity to the quantum realm, such as within black holes or at the moment of the Big Bang, it breaks down completely, producing nonsensical infinities. String theory, loop quantum gravity, and other attempts at unification offer tantalizing hints but remain unproven, as they require energy levels far beyond what our experiments can reach. What if the very structure of reality is such that these two fundamental theories will never be reconciled? That we are doomed to always see only fragments of a deeper, unreachable truth? Even our observational techniques impose fundamental limits on what we can learn. The observable universe is bounded by the cosmic horizon, the distance beyond which light has not had time to reach us since the beginning of time. Anything beyond this horizon, no matter how significant, is forever hidden from us. As the universe expands, this boundary grows. But paradoxically, so does the rate of expansion itself, meaning that some distant galaxies are actually moving away from us faster than the speed of light. This means that entire regions of the cosmos will become permanently inaccessible, their light never able to reach us. If there is something beyond our cosmic horizon, whether another universe, another set of physical laws, or even the true nature of reality itself, we may never be able to observe it directly. Could the greatest secrets of existence be locked behind a cosmic wall, always beyond our grasp? This limitation extends to the earliest moments of the universe itself. The further we look into space, the further we see back in time. But there is a hard limit, the point before which no light could escape. The cosmic microwave background radiation is the oldest light we can see, dating back to about 380,000 years after the Big Bang. But what happened before that? What if our very models of the Big Bang are wrong, and the universe had no singular beginning, but rather emerged from a prior state we have yet to comprehend? Some theories propose a cyclic universe, where each Big Bang is followed by a cosmic rebirth, while others suggest that the singularity was never truly a single point, but something even stranger, a bridge between different realities, or a transition from one phase of physics to another that we cannot yet perceive. If we can never observe beyond this limit, will we ever know for sure? Even our most successful theories contain paradoxes that suggest we may never reach a final answer. The information paradox of black holes, for example, presents a fundamental conflict between relativity and quantum mechanics. According to Einstein, nothing that falls into a black hole can escape. Yet quantum theory suggests that information can never truly be destroyed. If information is lost in black holes, it violates the laws of quantum mechanics. Yet if it somehow escapes, it challenges our understanding of space-time itself. Stephen Hawking famously proposed that black holes emit radiation and slowly evaporate over time. But what happens to the information trapped within? Does it leak out in a scrambled, unreadable form? Does it persist in some hidden dimension? Or is our entire framework for understanding black holes fundamentally flawed? As if these challenges were not enough, there is the possibility that the universe is fundamentally unknowable due to the nature of consciousness itself. Some interpretations of quantum mechanics, such as the observer effect, suggest that reality is not fully determined until it is observed. Could it be that the act of measurement itself changes what we are trying to understand? What if the universe exists in an indeterminate state and only takes form as we interact with it? If this is the case, then the final truth of the cosmos may be something that no sentient being can ever perceive, because perception itself shapes what is perceived. And finally, there is the simple fact that science is limited by human capability. No matter how much we learn, we are still bound by our physical senses, our cognitive abilities, and the tools we build. Could there be aspects of reality so alien to human thought that we simply cannot conceive of them, just as a fish in the ocean cannot comprehend the stars? Might there be higher dimensions, unknown forces, or deeper laws of physics that exist completely beyond our reach? If a final, complete theory of everything exists, will we ever have the mental capacity to understand it? The history of cosmology is one of discovery, but also of humility. Every time we think we have reached the edge of knowledge, a new frontier opens before us. Every time we attempt to draw a final boundary, we find it dissolving under closer scrutiny. Perhaps the greatest challenge of all is accepting that the universe may be structured in such a way that no single perspective, no single theory, no single moment of enlightenment will ever reveal the whole truth. We will always be chasing the next discovery, the next mystery, the next paradox. And yet, despite the impossibility of a final answer, the search itself is what drives us. Even if the true nature of the universe is forever beyond our grasp, the pursuit of understanding brings us closer to something even more profound, a recognition of our own place in this vast, endless reality, a realization that we are part of the mystery itself. If there is no final edge, no ultimate revelation, then perhaps the journey is the purpose, the endless pursuit of knowledge, the only certainty in an uncertain cosmos. The quest to define the universe's limits, its origin, its fate has sparked one of the most profound intellectual struggles in human history. For centuries, scientists, philosophers, and astronomers have sought to determine whether the cosmos has an edge, an ultimate boundary where reality ceases, or whether it extends infinitely, a concept equally perplexing and unsettling. The deeper we probe into the nature of space and time, the more we uncover contradictions, paradoxes, and competing theories that refuse to align. The conflict between different models of the universe is not simply an academic debate. It is a fundamental challenge to our perception of reality, a struggle between what we can observe and what we can logically infer. One of the most pressing tensions in modern cosmology lies in the debate between an infinite and a finite universe. If the universe is finite, what lies beyond its edge? Is there a true outside, a region where space itself no longer exists? And if it is infinite, does that mean it has always been so, stretching eternally in all directions with no beginning and no end? The idea of an infinite universe is deeply unsettling, as it suggests that everything that can happen has already happened, somewhere out there, in another region of space so distant we can never reach it. If reality is truly infinite, then countless versions of ourselves may exist, each playing out different possibilities of life, each doomed to repeat itself endlessly. Such a concept strains not only physics but also philosophy, forcing us to question the very nature of identity, choice, and existence. Competing with the infinite model is the idea of a finite but unbounded universe, a concept that seems paradoxical at first. If space is curved in such a way that it loops back on itself, much like the surface of a sphere but in higher dimensions, then one could, in theory, travel in a straight line forever and eventually return to the same point. This model, suggested by Einstein's theory of general relativity, resolves some of the paradoxes of an infinite universe while avoiding the need for a true edge. However, it raises its own challenges. What determines the shape of this cosmic curvature? And if the universe is finite, what mechanism set its size? Moreover, Observations of the cosmic microwave background radiation suggest that space appears flat on large scales, contradicting predictions of extreme curvature, leading some to believe the universe may indeed be infinite after all. The debate over infinity is further complicated by the struggle to reconcile the laws of quantum mechanics with general relativity. While general relativity describes gravity as the bending of spacetime, quantum mechanics suggests that at the smallest scales, reality is chaotic and governed by probabilities rather than fixed laws. When we attempt to apply relativity to the quantum realm, such as in the singularity of a black hole or the first moments of the Big Bang, the equations break down, producing meaningless infinities. String theory, one of the most ambitious attempts to unify these two frameworks, proposes that space itself is composed of tiny, vibrating strings rather than point-like particles, with extra dimensions that are curled up at scales beyond our detection. If true, this means the universe has a deeper structure that remains hidden from observation, suggesting that what we perceive as the limits of reality are merely projections of a higher dimensional cosmos. But without experimental proof, string theory remains speculative, leading some physicists to doubt whether we are even asking the right questions. A key battleground in this conflict is the search for the ultimate cosmic boundary. What lies beyond the observable universe? The cosmic microwave background radiation marks the farthest point we can see, the afterglow of the Big Bang stretching back 13.8 billion years. Beyond this, the universe remains hidden from us, not because it does not exist, but because its light has not had time to reach us. The observable universe, then, is not necessarily the entire universe, but merely the region we can access. Some theories suggest that beyond this horizon, the cosmos continues much as we see it, an extension of the same physical laws and structures. Others propose a more radical idea that beyond our horizon, the fundamental laws of physics may change, that different regions of the universe may operate under different conditions, leading to the possibility of a multiverse, where separate regions exist with entirely different sets of physical constants, possibly even different numbers of spatial dimensions. The multiverse hypothesis represents one of the greatest clashes in modern cosmology. Some argue that it is the logical extension of inflation theory, which suggests that space expanded exponentially in the first fraction of a second after the Big Bang. If inflation continues eternally in some regions, then our universe may be just one bubble among an infinite number, each with its own unique properties. However, critics argue that the multiverse is an unfalsifiable concept. It cannot be tested, measured, or observed, making it more of a philosophical idea than a scientific theory. If we cannot access these other universes, then does it matter whether they exist? Should physics concern itself only with what can be measured? Or should it pursue even the most speculative possibilities in the hope that one day evidence might emerge? Further complicating the search for the edge is the accelerating expansion of the universe, driven by dark energy. As galaxies recede from us faster and faster, the observable universe is shrinking in a meaningful sense. Regions that are visible to us today will one day slip beyond our reach, their light stretched to wavelengths so long that they become undetectable. This means that future astronomers, billions of years from now, may be unable to see the cosmic microwave background, may be unable to detect other galaxies, and may believe themselves to be alone in a dark, empty cosmos. If knowledge is limited by time as well as space, then what other truths might be slipping away, just beyond our reach? Even within our own galaxy, the limits of knowledge present themselves. The interiors of black holes, for instance, remain hidden by the event horizon, a point beyond which no information can escape. Theoretically, anything falling into a black hole is lost to the outside universe forever. But if information truly disappears, it contradicts quantum mechanics, which states that information must be conserved. This paradox, Hawking's information paradox, remains unresolved, highlighting the fundamental tensions between our deepest theories. If we cannot know what lies beyond the event horizon of a single black hole, how can we ever hope to define the edge of the entire universe? The pursuit of cosmology is, at its core, a struggle against the limits of perception and understanding. Every advance in technology brings new insights, but also new questions. The James Webb Space Telescope is revealing galaxies that challenge our models of early cosmic evolution, suggesting that our understanding of the first billion years of the universe may be incomplete. Observations of the cosmic microwave background continue to refine our measurements of dark matter and dark energy, yet fail to explain their true nature. The Large Hadron Collider searches for evidence of new physics beyond the standard model, but so far, nothing definitive has emerged. Are we missing a key piece of the puzzle, or are we simply reaching the natural limits of what we can observe? This conflict between what is observable and what is theoretical, between the finite and the infinite, between what we know and what we suspect defines modern cosmology. It is a battle not only between competing models, but between the very nature of scientific inquiry and the fundamental structure of reality itself. We may never find a final answer, a true edge, a last frontier where knowledge ceases and mystery takes over. But perhaps that is what makes the pursuit so compelling. Every discovery reshapes the battle, every paradox deepens the struggle, and every unanswered question reminds us that the greatest conflict of all is not between competing theories, but between humanity's insatiable curiosity and a universe that refuses to yield all of its secrets. If the universe has no edge, then the very foundation of how we perceive reality must shift. The idea of an infinite cosmos challenges not just our current understanding of physics, but also the way we frame existence itself. It forces us to confront questions that go beyond mere scientific inquiry, questions that touch on philosophy, meaning, and the limitations of human thought. What does it mean for something to have no boundary? If the universe has no edge, does that mean it has no true beginning or end? And if space is infinite, does that mean every possibility has already been realized somewhere out there? The consequences of this conflict between our expectations and the vast, unknowable nature of the cosmos are profound, shaking the very core of what we think we understand about existence. In physics, an infinite universe would challenge our most fundamental model. The standard Big Bang theory describes the universe as expanding from an initial singularity, a point of infinite density and temperature, where all known laws of physics break down. But if the universe is truly boundless, was there ever a single starting point? Could the cosmos have existed eternally in some form or another before the event we call the Big Bang? Some theories, such as the cyclic model, suggest that the universe undergoes endless cycles of expansion and contraction, eliminating the need for a singular creation moment. Others propose a quantum fluctuation in a pre-existing multiverse, meaning our universe was simply one of many to emerge from a chaotic quantum state. If this is true, then the question of an edge is meaningless, not because the universe extends forever, but because space and time themselves are emergent properties, not fundamental ones. If the universe is infinite, the implications for cosmology are staggering. One of the most immediate concerns is the concept of duplication. In an infinite space with a finite number of particle arrangements, every possible configuration of matter must repeat an infinite number of times. This means that somewhere in a distant region beyond our observable horizon, there is another version of Earth, an exact copy, down to the last molecule. And not just one, but an infinite number of them, each containing identical versions of you, living out the same experiences, making the same choices. But if the universe is infinite, there must also be versions of Earth, where things played out differently, where history diverged, where alternate possibilities unfolded. The idea that reality itself may be endlessly repeating, or that infinite versions of ourselves exist across the cosmos, is a concept that challenges our very sense of individuality and uniqueness. Beyond duplication, an infinite universe would mean that physics, as we understand it, is incomplete. Our current theories are built on the assumption that space and time have boundaries, perhaps not physical edges, but limitations imposed by the laws of nature. The discovery of an infinite universe would force us to reconsider the role of entropy, the fate of matter, and the nature of cosmic evolution. If space never ends, does time follow the same rule? Or does the universe still have a finite lifespan, destined to either expand into a cold, empty void or collapse in a fiery rebirth? These questions remain unanswered, but if we are forced to abandon the idea of a bounded cosmos, we may need a completely new framework of physics to describe it. The implications go beyond physics. They strike at the heart of human existence. If the universe is infinite, does that change the meaning of life? Throughout history, Many have found comfort in the idea that we are part of a grand, structured plana universe, with a purpose, a beginning, and an ultimate destination. But an infinite universe may have no predetermined direction. It may be chaotic, random, a vast expanse without an overarching goal. This raises existential questions. If there is no edge, no limit, then is there no purpose? Or is purpose something we must create for ourselves, independent of cosmic design? The idea of infinity also challenges religious and philosophical doctrines. Many belief systems are built on the idea of a finite world with a defined creation point, a universe that is ordered and guided. But an infinite cosmos, one with no true boundary, one in which countless versions of reality may exist, complicates these perspectives. If everything that can happen has already happened somewhere else, what does that say about free will? If there are infinite versions of you, does that diminish your significance? Or does it reinforce the idea that every choice matters, because every choice is being played out in some distant cosmic reflection? One of the most unsettling consequences of an infinite universe is the loss of an ultimate answer. If space has no edge, then our search for a final truth, a complete theory of everything, may be impossible. We may never reach a moment where we can say with certainty, this is how the universe works, and this is why it exists. Instead, every new discovery may only lead to deeper mysteries, each question giving rise to new questions in an unending chain of inquiry. Some scientists embrace this, arguing that science is a journey rather than a destination. Others find it troubling, suggesting that human curiosity is forever doomed to chase an unreachable horizon. But while an infinite universe challenges our current models, it also opens the door for new physics. If the cosmos is boundless, then we must reconsider fundamental forces, the role of extra dimensions, and the nature of space itself. Some physicists believe that higher dimensional theories, such as string theory, may offer insights into why space appears infinite while remaining mathematically consistent. Others suggest that new quantum models may provide a deeper understanding of the fabric of reality, one that does not rely on conventional boundaries. The very concept of an edge may need to be redefined not as a physical boundary, but as a limit to our knowledge, a threshold we are continually expanding. The struggle to define the universe has already led to some of the greatest scientific revolutions in history. The realization that the Earth was not the center of the cosmos overturned centuries of belief. The discovery of an expanding universe shattered the idea of a static, eternal cosmos. The identification of dark matter and dark energy introduced forces that defy our previous understanding of physics. If we now confront the idea of an infinite universe, we may be on the brink of yet another paradigm shift tone that requires us to rethink not only cosmology, but the very nature of existence itself. Yet, despite all the conflicts and contradictions, the search continues. Whether the universe is infinite or not, whether it has an edge or stretches forever, the pursuit of knowledge remains one of the defining traits of humanity. We may never reach the final answer, but perhaps that is not the point. Perhaps the significance lies in the act of searching, in the desire to push beyond the known, to challenge what we think we understand, and to embrace the unknown as an invitation rather than a barrier. In the end, an infinite universe does not diminish us. It elevates us. It places us in a grander, more mysterious cosmos than we ever imagined. One where the possibilities are endless, where the questions never end, and where each discovery only deepens our appreciation for the infinite complexity of reality. Whether or not we ever find the ultimate truth, the fact that we continue to seek it is, in itself, a testament to the boundless nature of human curiosity. The pursuit of understanding the universe has been marked by moments of profound revelation turning points, where our perception of reality has shifted, forcing us to rethink everything we thought we knew. These key scientific breakthroughs, each a step forward in unraveling the cosmos, have shaped the course of modern physics and cosmology, guiding us toward deeper, more complex questions. Some of these discoveries have reinforced our models of the universe, while others have exposed fundamental gaps in our knowledge, hinting at forces and structures we are only beginning to comprehend. Among these, the role of dark energy in shaping the cosmic expansion stands as one of the most significant discoveries of the modern era, fundamentally altering our understanding of the fate of the universe. At the same time, rapid advancements in technology, especially in observational astronomy, have pushed the boundaries of human capability, allowing us to witness the birth of galaxies, detect planets around distant stars, and peer back to the earliest moments of existence. Each of these revelations represents a turning point, a moment where the universe has whispered something new to us, challenging us to listen, adapt, and explore further. One of the most groundbreaking discoveries in cosmology came in 1998, when two independent teams of astronomers studying distant supernovae made a shocking observation. The universe was not just expanding, it was accelerating. This defied expectations. Until that point, it was assumed that the combined gravitational pull of all matter would gradually slow the expansion of the universe, potentially halting it or even reversing it into a future collapse. Instead, these observations indicated that some unknown force, something completely unaccounted for in previous models, was pushing space itself apart. This force became known as dark energy, and it now accounts for approximately 70% of the total energy density of the universe. Its nature remains one of the greatest mysteries in physics, but its effects are undeniable. If dark energy continues to dominate, the universe will not only keep expanding, but galaxies will move farther and farther apart until, in the distant future, the sky itself may grow dark, as the light from all but the closest stars becomes unreachable. The discovery of dark energy represented more than just a shift in our understanding of cosmic expansion. It shattered previous assumptions about the ultimate fate of the universe. Before this revelation, cosmologists debated whether the universe was open, closed, or flat, whether it would continue expanding forever, eventually contract, or reach some stable equilibrium. But dark energy introduced an entirely new possibility. A universe that not only expands indefinitely but does so at an ever-increasing rate. If this continues unchecked, it could lead to what some call the Big Rip scenario, where the fabric of space itself is torn apart in a future so distant that it stretches the limits of human imagination. Even more unsettling, the nature of dark energy remains entirely unknown. Is it a fundamental property of space itself, akin to Einstein's cosmological constant? Or does it represent some new, exotic form of energy that interacts with gravity in ways we do not yet understand? Some theories even suggest that dark energy is not a fixed force, but evolves over time, raising the possibility that cosmic expansion could change course in ways we cannot yet predict. While dark energy dominates the large-scale structure of the universe, technological advancements have allowed us to explore the cosmos in ever greater detail, pushing the limits of our knowledge. One of the most significant tools in this quest has been space-based telescopes, which have revolutionized our ability to observe distant galaxies, detect exoplanets, and analyze the early universe. The Hubble Space Telescope, launched in 1990, provided humanity with some of the most breathtaking images of the cosmos ever captured, revealing deep space structures billions of light-years away, tracing the life cycles of stars, and providing crucial data for understanding the universe's rate of expansion. But even Hubble's capabilities have been surpassed by its successor, the James Webb Space Telescope, JWST, which launched in 2021 and has since delivered some of the most detailed and transformative observations in modern astronomy. JWST's infrared capabilities allow it to see further back in time than any previous instrument, capturing light that has traveled for more than 13 billion years. One of its most surprising findings came early in its mission, the discovery of galaxies that formed much earlier than expected, some appearing only a few 100 million years after the Big Bang. These observations challenge existing models of galaxy formation, suggesting that either our understanding of early star formation is incomplete or that something fundamental about cosmic evolution is missing from our theories. This discovery raises urgent questions. Were the first galaxies different in structure from those we see today? Could the laws of physics themselves have operated differently in the early universe? Or is there a missing component, some unknown factor that explains how galaxies could have assembled so quickly? Beyond studying distant galaxies, space telescopes have also played a crucial role in the search for planets beyond our solar system. The Kepler and TESS missions have identified thousands of exoplanets, some in their stars' habitable zone regions where liquid water could exist, and life as we know it might be possible. The James Webb Space Telescope has begun to analyze the atmospheres of these worlds, searching for biosignatures chemical markers that might indicate biological activity. The discovery of an Earth-like planet with atmospheric signs of life would be one of the most profound moments in human history, redefining our understanding of our place in the universe. Yet, even if we do find evidence of life beyond Earth, it raises new questions. Would alien life share the same biochemical foundations as life on our planet? Or could it be based on entirely different principles? Could there be forms of intelligence that exist beyond our capacity to recognize them? Meanwhile, advancements in radio astronomy have provided another turning point, revealing strange and unexpected phenomena that defy easy explanation. The detection of fast radio bursts, intense, millisecond-long flashes of radio waves from deep space haze, puzzled scientists. Some appear to repeat, while others remain one-time events. Their origins remain uncertain, with theories ranging from neutron star collisions to highly magnetized pulsars, and even, in the most speculative interpretations, the possibility of advanced extraterrestrial technology. Additionally, the detection of gravitational waves in 2015 by the LIGO and Virgo observatories confirmed one of Einstein's last untested predictions, opening an entirely new way to observe the universe. These ripples in space-time, caused by massive cosmic events such as black hole mergers, provide insights into some of the most extreme environments in the cosmos, allowing us to probe gravity itself at its most intense. Each of these discoveries represents a moment where our understanding of the universe has shifted, revealing new layers of complexity and deepening the mysteries we face. Dark energy challenges our understanding of cosmic fate. The James Webb Space Telescope forces us to reconsider the formation of galaxies. The search for exoplanets brings us closer to answering the age-old question of whether we are alone. And gravitational wave detection provides a new tool for exploring unseen cosmic events. But each revelation also brings new tensions, new contradictions, and new puzzles. If dark energy is a fundamental force of nature, what does that mean for the laws of physics as we currently understand them? If galaxies formed faster than our models predict, what assumptions are we getting wrong? If we do detect alien life, will we be ready for what that means for human identity, culture, and philosophy? Perhaps the most profound implication of these scientific turning points is the realization that our models of the universe are still incomplete. We stand on the edge of knowledge, peering into the unknown, armed with powerful tools yet still facing mysteries that seem insurmountable. With every discovery, the universe grows more complex, more intriguing, and more challenging to define. But this is not a reason for despair, it is a reason for excitement. The greatest revolutions in science have come from moments of uncertainty, from times when the old models no longer fit, and a new framework was needed to explain the cosmos. We may never reach a final answer, a complete and total understanding of the universe. But that is the nature of exploration. It is not the certainty of conclusions that drives us forward, but the endless pursuit of deeper truths. The universe continues to reveal its secrets, piece by piece, turning point by turning point, and each new revelation brings us one step closer to seeing the bigger picture, even if that picture remains forever unfinished. For centuries, humanity has approached the universe as something external in object to be measured, observed, and understood, using the frameworks of classical physics and, more recently, relativistic and quantum theories. We have sought to define its boundaries, uncover its fundamental laws, and determine whether it has an edge or extends into infinity. But what if we are looking at the problem the wrong way? What if our assumptions about space, time, and reality itself are flawed, limiting our ability to perceive the true nature of the cosmos? Throughout history, some of the greatest scientific breakthroughs have not come from new data alone, but from shifts in perspective or radical reimaginings of the fundamental principles guiding our understanding. Theories such as the holographic principle, quantum gravity, and emergent space-time challenge traditional cosmology, suggesting that the universe may not be what it appears to be, and that by shifting our perspective, we may unlock answers that have remained elusive for generations. One of the most provocative ideas in modern physics is the holographic principle, a concept that suggests the universe may be fundamentally two-dimensional, with what we perceive as three-dimensional reality being an emergent illusion, much like a hologram. This idea stems from studies of black holes and entropy. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered that the amount of information or entropy that can be contained within a black hole is proportional not to its volume, as one might expect, but to the surface area of its event horizon. This led to the shocking realization that all the information about the contents of a black hole could, in theory, be encoded on its two-dimensional boundary. If this is true for black holes, then some physicists, notably Gerard Hooft and Leonard Susskind, have proposed that the same principle may apply to the entire universe. In other words, everything we experience as three-dimensional, including space itself, may actually be encoded on a two-dimensional surface at the edge of the cosmos. This would fundamentally change how we perceive space and time. If the holographic principle is correct, then asking whether the universe has an edge may be an ill-posed question, because the very concept of three-dimensional space might be emergent rather than fundamental. Instead of thinking of the universe as an expanding physical structure, we might need to conceive of it as a vast projection of quantum information, much like a computer-generated simulation. This doesn't mean we are living in a literal simulation, but it does imply that our reality is not as solid and tangible as classical physics suggests. Instead, the fundamental nature of the universe may be deeply intertwined with information theory, quantum entanglement, and principles that defy conventional understanding. Quantum mechanics itself offers another paradigm shift, one that has yet to be fully integrated into cosmology. Classical physics assumes that the universe is made of discrete object stars, planets, galaxies, all existing within a well-defined space-time framework. But quantum mechanics suggests something radically different, that reality, at its most fundamental level, does not consist of separate, independent objects but of probability waves, superpositions, and entangled states that defy classical logic. If this is true on the scale of atoms and particles, could it also be true for the structure of the universe as a whole? Could the cosmos exist not as a fixed and deterministic entity, but as a superposition of multiple possible states, each coexisting in a vast, interconnected quantum system? One of the most striking examples of this perspective shift comes from the observer effect in quantum mechanics. Experiments, such as the double-slit experiment, suggest that particles behave differently when observed than when they are left unmeasured. If this principle applies at the macroscopic level, it raises profound questions about the nature of the cosmos. Could it be that the act of observation itself plays a role in shaping reality? If so, then our entire approach to cosmology, where we assume that the universe exists in a fixed, independent state, may need to be revised. Some interpretations of quantum mechanics, such as the many worlds interpretation, even suggest that every possible outcome of every quantum event is realized in separate, parallel universes. This would mean that what we perceive as the universe is only one of an infinite number of possible realities, all existing simultaneously but beyond our reach. If space-time itself is an emergent property rather than a fundamental one, then our understanding of cosmic expansion must also change. Currently, we describe the universe as expanding because distant galaxies are receding from us due to the effects of dark energy. But what if this expansion is not movement in space, but the result of a deeper process related to quantum information? Some theories suggest that what we call the expansion of the universe is actually the growth of entropy, a gradual unfolding of quantum states that gives rise to the illusion of space stretching outward. If this is true, then the question of whether the universe is finite or infinite may be misleading, because space itself may not be a fundamental aspect of reality at all. These radical shifts in perspective also reshape discussions around the origin of the universe. The traditional Big Bang model suggests that the cosmos emerged from an initial singularity, an infinitely dense and hot point where all known laws of physics break down. But if space-time is emergent, then the Big Bang may not have been a singular beginning, but rather a transition from one phase of quantum information to another. Some physicists propose that the universe began as a quantum fluctuation within a larger pre-existing quantum systemon that may have no beginning or end, existing in a perpetual cycle of creation and transformation. Others suggest that what we perceive as the Big Bang was merely one bounce in an endless sequence of cosmic cycles, where universes are born, expand, and contract repeatedly over infinite time. The implications of these ideas stretch beyond science into philosophy. If reality is a quantum projection, then what does that mean for our understanding of existence? If space and time are emergent, then what does that say about consciousness, identity, and free will? Are we simply localized patterns within a vast informational structure? And if the cosmos exists as a quantum superposition, does that mean that all possible versions of reality, including different versions of ourselves, coexist in a vast multiversal web? Shifting perspectives has always been a crucial driver of scientific progress. In ancient times, humanity believed that Earth was the center of the universe, a notion that was overturned by Copernicus. Later, Newton provided a deterministic framework of the cosmos, which was revolutionized by Einstein's relativity, showing that space and time were fluid rather than absolute. Now, as we move further into the quantum age, it is becoming clear that even relativity is not the final answer, and that deeper layers of reality remain hidden beneath the surface of our current models. Perhaps the key to understanding the universe is not simply to build more powerful telescopes or conduct more experiments, but to fundamentally rethink our approach. Instead of treating space as an expanding container, we might need to view it as a dynamic, emergent property of quantum interactions. Instead of searching for a physical edge to the cosmos, we might need to redefine what an edge even means in the context of higher dimensional space. Instead of assuming that the laws of physics are fixed and universal, we might need to consider the possibility that they too are emergent, shaped by the conditions of our specific cosmic region. In the end, the search for answers may require us to abandon long-held assumptions and embrace the possibility that reality is stranger, more complex, and more interconnected than we ever imagined. The next great breakthrough in cosmology may not come from a new observation or an experiment, but from a shift in the way we ask questions, from looking beyond the visible and tangible, and instead, considering the possibility that the universe itself is not what it seems. Throughout history, every major scientific revolution has been accompanied by a moment of unexpected realization and instance, where the prevailing theories of the time were upended by discoveries that no one could have anticipated. Time and time again, the universe has defied our expectations, forcing us to abandon old assumptions and embrace radical new ideas. Today, we find ourselves on the precipice of yet another shift in understanding, one that challenges the very nature of reality itself. From the bizarre implications of multiverse theories to the mind-bending possibility that we live in a simulation, modern cosmology is confronting ideas so strange that they threaten to dismantle everything we thought we knew about our place in the cosmos. What if the fundamental nature of the universe is not what it appears to be? What if the reality we experience is only a fragment of something far greater, something stranger than even our wildest theories have imagined? One of the most unexpected twists in modern physics has been the growing evidence for the multiverse hypothesis, the idea that our universe is just one of many, perhaps an infinite number, each existing with its own set of physical laws, dimensions, and possibilities. At first, the notion of multiple universes seemed like little more than speculation, a philosophical exercise rather than a serious scientific concept. But as researchers delved deeper into the fundamental laws of physics, they began to find hints that our universe may not be the only one. The strongest argument for the multiverse arises from cosmic inflation, the rapid expansion of space that occurred in the first fraction of a second after the Big Bang. According to inflationary models, space itself is constantly expanding at an exponential rate, and in some regions, this expansion never stops, creating countless bubble universes, each with its own version of physics. If this is true, then the very question of whether our universe has an edge or is infinite becomes irrelevant, because beyond what we can observe, entirely different realities may be unfolding, governed by forces and principles we cannot even imagine. Some of these universes may be similar to ours, differing only in the arrangement of galaxies or the outcomes of quantum events. Others may be radically different, with different numbers of spatial dimensions, different fundamental particles, or even laws of physics so alien that they are incomprehensible to us. This possibility forces us to reconsider everything we know about the uniqueness of our own cosmos. If there are infinite universes, then is our existence truly special? Or are we just one among countless versions of reality? The implications of the multiverse go far beyond physics. They challenge the very foundations of human thought. If everything that can possibly happen does happen somewhere in the multiverse, then does free will truly exist? Every choice we make, every decision that shapes our lives, could simply be one branch of an infinite number of possible outcomes, all playing out simultaneously across the multiverse. Somewhere out there, another version of you may have taken a different path, lived a different life, experienced a different history. Does this diminish the significance of our experiences, or does it reinforce the idea that every moment, no matter how small, contributes to a vast, interconnected web of possibilities? Even more unsettling is the idea that the laws of physics themselves may not be as fundamental as we assume. If different universes operate under different laws, then the physical constants that govern our reality, such as the speed of light, the strength of gravity, or the masses of fundamental particles, may be arbitrary, set by chance, or by some deeper mechanism we do not yet understand. This raises profound questions about why our universe appears to be so finely tuned for life. Some physicists argue that this is simply a selection effect. We find ourselves in a universe that supports life because, by definition, we could not exist in one that did not. But others suggest a more radical possibility, that the very structure of the cosmos is not random, but instead follows principles of self-organization, where universes that develop complexity and intelligence are more likely to persist. This leads directly to an even more unsettling idea: the simulation hypothesis. Originally proposed by philosopher Nick Bostrom, this theory suggests that if advanced civilizations are capable of creating detailed simulations of reality, then it is statistically more likely that we are living in one of those simulations than in the base reality. The logic is straightforward. If a civilization reaches a level of technological advancement where it can create highly realistic, conscious simulations, then it could create an enormous number of such simulated worlds, potentially billions or even trillions. If that is the case, then the probability that our reality is the original, physical one is incredibly low. Instead, we may be living in an artificial construct, a virtual environment designed by an unknown intelligence. While this idea may sound like science fiction, it has been taken seriously by some leading physicists and technologists. Elon Musk has famously argued that the odds of us living in a base reality are 1 in billions. Some researchers have even proposed ways to test the hypothesis, such as looking for evidence of computational limits within the fabric of spacetime, or detecting anomalies that suggest our universe is running on an underlying code. While no definitive proof has been found, the mere possibility forces us to reconsider everything about our existence. If we are in a simulation, who or what created it, and for what purpose? Are we simply an experiment, a form of entertainment, or something else entirely? Could our simulated reality be one of many, each testing different variations of physics, life, or intelligence? The deeper we probe into these questions, the more we are forced to confront the limitations of human understanding. Whether through the multiverse, the simulation hypothesis, or yet another paradigm-shifting discovery, we are beginning to see that our place in the cosmos is not what we once thought. The comforting notion of a singular knowable universe has been replaced by a vast and bewildering landscape of possibilities, each more mind-bending than the last. The unexpected twist in our search for cosmic truth is that the universe may be even stranger than we ever imagined, not just vast, but layered with hidden structures, alternate realities, and fundamental principles that we have yet to grasp. Perhaps the most profound realization of all is that we may never have a final answer. The quest to understand the cosmos may be an endless journey, with each new discovery leading only to deeper mysteries. And yet, this does not diminish the value of the pursuit of anything. It makes it even more meaningful. The fact that we are able to ask these questions at all, that we are capable of contemplating our own existence and challenging our own assumptions, is itself an extraordinary achievement. Whether we are living in a multiverse, a simulation, or a reality even more complex than we can currently conceive, one thing remains true. Our curiosity, our desire to explore, and our ability to push the boundaries of knowledge are among the most remarkable qualities of our species. The universe continues to surprise us, to defy our expectations, and to challenge our understanding in ways we never anticipated. And as we stand on the edge of discovery, staring into the unknown, we are reminded of the most important lesson of all, that the greatest mysteries are not obstacles, but invitations to think deeper, to question more boldly, and to embrace the infinite possibilities that lie before us. As we push further into the cosmos, seeking answers to the universe's greatest mysteries, we find ourselves facing an array of daunting challenges. Despite the groundbreaking discoveries of recent decades, dark energy, exoplanets, gravitational waves, and the hints of a multiverse, many of the most fundamental questions remain unanswered. What is the true nature of dark matter and dark energy? What lies beyond the observable universe? Could there be extra dimensions, parallel realities, or entirely new laws of physics waiting to be uncovered? And most fundamentally, will we ever have the tools to find out? The pursuit of cosmic truth is constrained by both technological and theoretical limitations, and overcoming these hurdles will require not only new ideas, but also new instruments, new methods, and a reimagining of how we explore the universe. The limitations of current observational technology. One of the greatest challenges facing modern cosmology is the limit of observation. The fact that we can only see so far, only detect so much, and only measure within the constraints of our technology. The cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang, places a fundamental boundary on what we can observe. Even with our most advanced telescopes, we cannot see beyond this limit, because light from beyond has simply not had time to reach us. This means that, no matter how much our instruments improve, certain regions of the universe will forever remain hidden. If something truly exotic exists beyond our observable universe, perhaps regions with different laws of physics, or the evidence of a multiverse, we may never be able to detect it directly. Even within the observable universe, we are limited by the wavelengths of light we can detect. Optical telescopes like Hubble have provided breathtaking images of distant galaxies, but they are constrained by the properties of visible light. Many of the universe's deepest secrets, such as the earliest moments after the Big Bang, the interiors of black holes, or the distribution of dark matter, require different methods of observation. Radio telescopes, X-ray detectors, and gravitational wave observatories have expanded our capabilities, but they are still in their infancy compared to what will be needed to truly revolutionize our understanding. Perhaps the most pressing issue is our inability to directly observe dark matter and dark energy. Despite accounting for roughly 95% of the universe's total energy and mass, these mysterious components remain invisible, detected only through their gravitational effects. If we cannot see them, cannot touch them, and cannot interact with them directly, how can we ever truly understand what they are? Current experiments, such as the Large Hadron Collider, LHC, and underground dark matter detectors, have so far failed to produce definitive results. Future efforts will need to go beyond what we currently have, pushing into entirely new realms of physics. The need for next-generation space missions. Given these challenges, the next major leap in cosmic exploration will depend on next-generation space missions, more advanced telescopes, deeper space probes, and entirely new ways of measuring the universe. The James Webb Space Telescope, JWST, is just the beginning. Already, it has begun peering deeper into space than ever before, revealing galaxies that formed surprisingly early in the universe's history and challenging current models of cosmic evolution. But even JWST has its limitations. To truly push the boundaries, we will need telescopes with even greater sensitivity, capable of detecting faint signals from the first moments after the Big Bang, mapping dark matter with unprecedented precision, and analyzing the atmospheres of distant exoplanets in search of life. The next generation of space telescopes, the planned Nancy Grace Roman Space Telescope, will take a significant step forward in dark energy research, using advanced techniques to map the universe's large-scale structure and track cosmic expansion over time. Beyond that, proposals such as the LUVOIR, Large Ultraviolet Optical Infrared Surveyor, and HABEX, Habitable Exoplanet Observatory, aim to detect Earth-like planets around other stars, directly imaging their surfaces and searching for biosignatures in their atmospheres. These missions could provide definitive proof of extraterrestrial life, answering one of humanity's most profound questions. Even more ambitious are concepts like the LISA, Laser Interferometer Space Antenna mission, which will detect low-frequency gravitational waves from supermassive black hole collisions and possibly even ripples from the Big Bang itself. These waves could reveal structures of the universe that have remained hidden, allowing us to explore the fundamental nature of space-time at an entirely new level. And then, there are missions to explore the solar system and beyond. The upcoming Europa Clipper and Dragonfly missions will search for life in the subsurface oceans of Europa and Titan, moons of Jupiter and Saturn that may harbor conditions suitable for biology. At the same time, Breakthrough Starshot, a project backed by physicists such as Stephen Hawking before his passing, aims to send tiny, laser-propelled probes to the Alpha Centauri system at 20% the speed of light, potentially reaching another star system within our lifetime. If successful, it would represent the first step toward interstellar exploration. The search for new physics. One of the biggest uncertainties in modern cosmology is that our current models of physics are incomplete. The standard model of particle physics, while successful in many respects, fails to explain dark matter, dark energy, and the origin of mass itself. Meanwhile, general relativity, our best theory of gravity, breaks down at the quantum scale and inside black holes, suggesting that a deeper, more fundamental theory is needed. Some of the most promising avenues for new physics include the search for new particles. The Large Hadron Collider has probed the smallest known scales of matter, but so far, it has not found evidence of supersymmetry or other proposed extensions to the standard model. New accelerators, such as the proposed Future Circular Collider, could reach even higher energy levels, probing physics beyond what we currently know. Quantum gravity. The unification of quantum mechanics and general relativity remains one of the greatest unsolved problems in physics. Theories such as string theory and loop quantum gravity attempt to bridge this gap, but they remain untested. Advances in observational astrophysics, such as detailed studies of black hole event horizons, may provide clues to how gravity behaves at the smallest scales. The nature of dark matter. While current dark matter searches have yielded no direct detections, next-generation experiments such as the Senate detector and Darwin experiment may finally confirm or rule out certain classes of dark matter candidates. If dark matter turns out to be something even stranger than expected, it could lead to an entirely new understanding of the fundamental forces of nature. How scientists plan to tackle the biggest questions. Despite these challenges, researchers are not deterred. The next decade of cosmology will focus on tackling the biggest unanswered questions using a combination of improved technology, new experimental techniques, and interdisciplinary collaboration. Some of the key strategies include building larger and more sensitive detectors to probe dark matter, gravitational waves, and high-energy cosmic events, developing AI and machine learning algorithms to sift through massive amounts of astronomical data, identifying patterns and anomalies that human researchers might miss, expanding international collaboration, as projects like the Square Kilometre Array, SKA, telescopy multinational effort to build the world's largest radio telescope demonstrate the power of working across borders, simulating the universe using supercomputers, allowing scientists to model cosmic evolution with unprecedented accuracy and test different theories against observational data. The future of cosmic exploration. Despite the hurdles that remain, we stand at a turning point in human history. The next few decades will bring answers to some of the greatest mysteries ever posed and, inevitably, will raise new questions. Whether we discover extraterrestrial life, unlock the secrets of dark energy, or even glimpse the true nature of the multiverse, one thing is certain: the quest for knowledge is far from over. As we continue this grand exploration, we must acknowledge that there may be limits to what we can ever truly know. The universe may hold secrets beyond human comprehension, questions that no amount of technological advancement will ever fully answer. But this should not be a cause for discouragement, rather. It should be a source of inspiration. The fact that we can even attempt to unravel these cosmic mysteries is itself a triumph of human curiosity and determination. Whether or not we ever find the ultimate answer, the journey itself, the relentless pursuit of understanding, the willingness to challenge old ideas and embrace new ones is what defines us as a species. And so, we press on, deeper into the cosmos, further into the unknown. The universe is waiting. The quest to understand the universe has always been driven by conflicting ideas, by a tug of war between theories that explain part of the picture but never quite the whole. We are at a crossroads in cosmology where some of the most fundamental questions remain unanswered. and competing models challenge one another in a battle for dominance. The latest theories seek to redefine our understanding of space, time, and the very fabric of existence. The debate continues. Will we ever find a true boundary to the universe? Or is the search for an edge a misguided effort? Can we unify general relativity with quantum mechanics, creating a complete theory of everything? Or are we forever doomed to see only fragments of a larger truth? This is the final confrontation, the clash between our best scientific models and the limits of what we can perceive. The latest competing theories, searching for the ultimate model. At the forefront of cosmology, several competing theories attempt to explain the deepest mysteries of the universe. Each has its strengths, yet none has emerged as the definitive answer. The greatest challenge is bridging the two most successful frameworks in modern physics: general relativity, which describes gravity and the structure of space-time, and quantum mechanics, which governs the behavior of particles at the smallest scales. These two theories, despite their success, remain fundamentally incompatible when applied to the extremes of black holes or the origins of the universe. String theory and the holographic universe. One of the most ambitious attempts to unify physics, string theory, suggests that all particles and forces arise from tiny vibrating strings existing in higher dimensions beyond the three spatial dimensions we experience. String theory provides a potential framework where gravity and quantum mechanics coexist, but it comes with a major problem: it requires extra dimensions that have never been observed. Proponents argue that these hidden dimensions could be compactified at microscopic scales. But skeptics question whether a theory that relies on untestable components can truly be considered scientific. String theory also gave rise to the holographic principle, which proposes that our three-dimensional universe is actually a projection of information encoded on a two-dimensional boundary. If this idea is correct, then the edge of the universe may not be a physical boundary, but a limit to how much information can be stored within spacetime. This radical shift in perspective suggests that what we experience as reality could be akin to a hologram emergent structure derived from fundamental quantum information, loop quantum gravity, and the end of singularities. Another contender in the unification battle is loop quantum gravity, LQG, which attempts to quantize spacetime itself. Unlike string theory, which relies on extra dimensions, LQG suggests that space is made of discrete, indivisible loops, creating a fundamentally granular structure to the universe. One of the most exciting predictions of LQG is that it eliminates singularities, meaning that black holes and the Big Bang may not be true points of infinite density, but instead transitions into new states of matter and energy. If this is true, it changes the question of whether the universe has an edge. Instead of a singular beginning at the Big Bang, the universe may have undergone a bounce transition from a previous state, implying an eternal cycle of cosmic births and deaths. The multiverse hypothesis. If the idea of an edge to the universe is problematic, then the multiverse hypothesis offers a way out. It suggests that our universe is just one of many, with countless others existing beyond our reach. Some of these universes may be entirely different, with different physical laws, while others may be nearly identical to our own. The leading evidence for the multiverse comes from cosmic inflation, the theory that space expanded exponentially in the first moments after the Big Bang. Inflationary models predict that certain regions of space should continue inflating indefinitely, creating an infinite number of pocket universes. But if we live in a multiverse, can we ever confirm its existence? If we can never observe these other universes, then is the question of an edge even meaningful? The challenge of proving the multiverse makes it a controversial topicone that could either redefine physics or remain forever in the realm of speculation. The ongoing debate: will we ever find a true boundary? With so many competing theories, the question remains: is there a true boundary to the universe? One possibility is that the universe is finite but unbounded, meaning that it has a limited size but no edge like the surface of a sphere, but in higher dimensions. If this is the case, then traveling far enough in one direction would eventually bring you back to your starting point, much like circumnavigating the Earth. This aligns with some interpretations of relativity, suggesting that space could be curved on the largest scales. Another possibility is that the universe is truly infinite, extending forever, with no boundary. If this is true, then the concept of an edge is meaningless. This raises profound philosophical and scientific questions. If the universe is infinite, does that mean every possible arrangement of matter has already occurred somewhere? Does infinity imply that every version of ourselves exists somewhere in space? A third possibility is that we are simply asking the wrong question. If the holographic principle is correct, then what we perceive as space may not be fundamental at all. Instead, the universe could be an emergent property of deeper quantum structures, meaning that an edge is not a physical location, but a limit on the information that can be processed within space-time. Unifying physics, the greatest challenge of our time. The battle to unify general relativity and quantum mechanics represents the greatest unresolved challenge in modern physics. These two theories have shaped our understanding of reality, yet they remain deeply incompatible in extreme environments like black holes and the Big Bang. Efforts to bridge this gap include quantum gravity approaches, such as string theory and loop quantum gravity, which attempt to merge space-time with quantum principles. Holography, which suggests that gravity and space emerge from lower-dimensional quantum information. New experimental physics, such as gravitational wave observatories and high-energy particle experiments, which may provide data to test these theories. The future of cosmology. What comes next? Despite the unresolved conflicts, cosmology is on the verge of a new era. Future telescopes and experiments will push the limits of observation, offering potential breakthroughs in detecting dark matter. Next, generation particle detectors and space-based observatories may finally reveal what dark matter is made of. Measuring dark energy. The Vera C. Rubin Observatory and future deep space missions will refine our understanding of cosmic acceleration. Probing black holes. Improved observations of black hole mergers and event horizons may reveal quantum gravity effects. Exploring exoplanets. Advanced telescopes will search for biosignatures in alien atmospheres, potentially answering the question of extraterrestrial life. At the same time, theoretical breakthroughs may come from unexpected places. Just as Einstein revolutionized physics with relativity and quantum mechanics overturned classical assumptions, the next great leap may arise from a shift in how we define reality itself. The ultimate question: can we ever know everything? As much as we have learned, the greatest cosmic mystery remains. Is there a final theory of everything? Will we one day discover a set of laws that fully describe reality? Or is the universe fundamentally unknowable? Perhaps the most unsettling possibility is that there are limits to human knowledge, that some aspects of the cosmos are forever beyond our reach. If we live in a holographic universe, then there may be an ultimate resolution limit, preventing us from seeing beyond a certain scale. If the multiverse is real, then we may be confined to a single pocket, never able to explore the full extent of existence. But maybe that is not a failure, it is part of the beauty of the search itself. The universe, in all its complexity, is not just something to be solved, but something to be explored, experienced, and continually questioned. The final confrontation between competing theories may never produce a single victor, but instead, an ever-expanding understanding of our place in the cosmos. And so, we press forward toward deeper mysteries, toward uncharted realms of physics, and toward the realization that the greatest journey of all is the pursuit of the unknown. The pursuit of cosmic knowledge is more than a scientific endeavor. It is a reflection of humanity's deepest instincts, a testament to our unrelenting curiosity and our desire to understand the nature of existence. From ancient civilizations mapping the stars to modern physicists probing the quantum fabric of reality, our species has always been driven by a need to explore, to question, and to push beyond the boundaries of the known. But in our search for answers, we are confronted by a paradox. The more we learn, the more we realize how little we truly understand. With each discovery, the universe reveals itself to be more complex, more mysterious, and more awe-inspiring than we ever imagined. This balance between knowledge and mystery is not a flaw in our understanding. It is an essential part of the human experience, a reminder that some truths may forever remain just beyond our grasp. The deeper meaning of exploring the unknown. To explore the unknown is to embrace uncertainty. It is to acknowledge that the universe does not owe us simple explanations, that reality is not structured for our convenience. And yet, we explore anyway. We climb mountains without knowing what lies beyond the next peak. We dive into the deepest oceans without being certain of what we will find. And we gaze into the vastness of space, driven not by necessity, but by an instinctual pull toward discovery. What is it that compels us to reach for knowledge that may never be fully within our grasp? At its core, the search for cosmic truth is a reflection of something deeply human: the need to understand our place in the grand scheme of existence. Are we alone in the universe? Did the cosmos emerge from nothing? Or has it always existed? Is there an ultimate boundary to reality? Or is space infinite, stretching on with no end? These questions are not just scientific inquiries. They are existential ones. They define our sense of identity, our understanding of purpose, and our relationship with the unknown. Whether or not we ever find definitive answers, the very act of asking these questions expands the way we think, pushing us beyond the limitations of our immediate existence. The universe is vast, cold, and indifferent. Yet within it, we find meaning not because it is given to us, but because we create it. The stars do not care about us, but we care about them. We write poetry about them, navigate by them, and use them to measure time itself. In this way, the cosmos is not just a distant, unreachable expansite, it is a mirror, reflecting back our deepest desires, our greatest ambitions, and our unbreakable need to explore. How curiosity drives scientific progress. Every major leap in human understanding has been fueled by curiosity. It is the driving force behind every great discovery, every groundbreaking theory, every technological innovation. It was curiosity that led early humans to track the movements of celestial bodies, to develop calendars, and to recognize patterns in the stars. It was curiosity that led Galileo to turn his telescope to the heavens, revealing moons orbiting Jupiter and mountains on the moon, shattering the illusion that Earth was the center of everything. It was curiosity that drove Einstein to rethink the nature of time and space, revolutionizing our understanding of gravity. And today, it is curiosity that propels us into the cosmos, pushing us to send probes to other planets, to search for life beyond Earth, and to decode the structure of the universe itself. But curiosity is not just about acquiring knowledge, it is about challenging assumptions. Every great scientific revolution has required us to let go of previous ideas, to recognize that what we once believed to be true was merely an incomplete picture. The shift from a geocentric to a heliocentric model of the solar system was met with resistance, not because the evidence was lacking, but because it required a fundamental change in perspective. Similarly, the idea that space and time are not absolute, but relative, defied intuition when Einstein first proposed it. And today, as we consider theories of a multiverse, extra dimensions, or the possibility that reality itself is a quantum hologram, we must once again confront the possibility that our current understanding is only a fraction of the truth. Curiosity demands that we ask uncomfortable questions, that we embrace the possibility of being wrong, and that we remain open to ideas that challenge everything we thought we knew. It is not a passive trait, it is an active force, one that drives progress forward even in the face of uncertainty. The balance between knowledge and mystery. In our pursuit of knowledge, we must also recognize the value of mystery. There is an inherent tension between our desire to explain everything and the realization that some questions may never have clear answers. This is not a failure of science, it is a fundamental characteristic of the universe itself. The cosmos is not a puzzle to be solved with a single final answer. It is a continuous unfolding of deeper and deeper layers of complexity. For every discovery we make, new mysteries emerge. We once believed the universe was static, only to learn that it is expanding. We then assumed this expansion was slowing down, only to find that it is accelerating due to an unknown force we call dark energy. We thought black holes were regions of absolute darkness, only to discover that they radiate energy and may even hold clues to the nature of quantum gravity. Each revelation leads not to closure, but to new frontiers of exploration. This interplay between knowledge and mystery is what keeps science alive. If we knew everything, if there were no more questions to ask, then curiosity would cease to exist. But the universe ensures that this will never happen. No matter how much we learn, there will always be deeper layers waiting to be uncovered. In this way, the greatest lesson we can learn from cosmic exploration is humility. The universe is vast, beyond comprehension, and our place within it is fleeting. And yet, despite our smallness, we are capable of understanding its laws, of decoding its secrets, and of asking questions that extend beyond the limits of our immediate experience. The realization that we will never know everything does not diminish it elevates us. It means that the journey will never end, that there will always be more to explore, more to understand, more to question. Lessons humanity can learn from cosmic exploration. The study of the universe is not just an academic pursuit, it carries profound moral and philosophical implications. It teaches us about perspective, reminding us that the divisions and conflicts we create on Earth are insignificant in the grand scheme of existence. From space, national borders disappear, political struggles fade, and what remains is a single, fragile planet, home to all known life. The realization that we are all passengers on the same cosmic journey should inspire unity, cooperation, and a sense of shared purpose. Cosmic exploration also teaches us about resilience. The universe is an unforgiving place, yet, against all odds, life emerged on Earth. The atoms in our bodies were forged in the hearts of ancient stars, scattered across space by supernovae, and assembled through billions of years of evolution. We are not separate from the cosmos, we're a product of it, a way for the universe to know itself. This perspective should fill us with a sense of responsibility. If life is rare, if intelligence is even rarer, then we have a duty to preserve it, to protect our planet, and to seek knowledge not just for ourselves, but for the generations that will follow. Perhaps the most important lesson is that exploration is its own reward. We may never find the ultimate answer to why the universe exists, or whether it has a true edge, or what lies beyond our observable horizon. But the pursuit of these questions is what makes us human. We do not seek knowledge simply for the sake of answers. We seek it because it is in our nature to do so. In the end, the greatest discovery of all may not be found in the distant reaches of the cosmos, but within ourselves. The realization that the journey of exploration, the act of questioning, and the wonder of the unknown are what give meaning to our existence. The universe will always be full of mysteries, but as long as we continue to ask, to seek, and to dream, we will always be a part of its unfolding story. The ultimate question in any great pursuit of knowledge is whether we will ever reach a final answer, or if the nature of reality itself ensures that mystery will always remain. As we explore the universe, we uncover layers of complexity so deep that each revelation brings more questions, more possibilities, and more unknowns. Should the search for the ultimate truth have a closed conclusion where we eventually find all the answers, map the final boundaries of space, and define existence with certainty? Or should the mystery remain open-ended, forever pulling us toward new horizons, always hinting that there is something more to discover? The value of leaving questions unanswered is not a weakness of science, but its greatest strength. It is the very reason we continue to explore, to challenge, to wonder. The value of leaving questions unanswered. At first, the idea of an open-ended mystery might seem unsettling. We are wired to seek closure, to find order in chaos, to solve problems and put them to rest. Yet, the universe resists this impulse. Every time we think we have reached the final layer of understanding, we find that it was merely a gateway to something deeper. The nature of space-time, the limits of observation, the structure of matter. None of these questions have led to simple, final answers. Instead, they have revealed new frontiers, new anomalies, and new fundamental uncertainties. Perhaps this is not an accident. Perhaps the very structure of reality is designed in such a way that knowledge is always expanding, that there is no final destination, only an eternal unfolding of possibilities. If we were to ever solve the universe, if every question had an answer, and every law of physics was complete, then what would be left to explore? The pursuit of knowledge is what defines it, is what separates us from mere existence. The unknown is not a flaw in our understanding. It is what keeps the journey alive. One of the most profound lessons from cosmic exploration is that not knowing is what makes discovery meaningful. If the universe were simple, if it fit neatly within human comprehension, it would not inspire the sense of wonder that it does. The mystery of what lies beyond the observable universe, the paradoxes of quantum mechanics, the nature of dark energies are not failures of science, but invitations to go further. They remind us that knowledge is never truly final, that reality is always more intricate than we initially assume. Summary of the biggest takeaways. As we have explored the vastness of the cosmos, several major themes have emerged, each reinforcing the idea that the pursuit of understanding is as infinite as the universe itself. The universe is more mysterious than we ever imagined. Every breakthrough in science has not simplified our understanding of the universe, but has made it more complex. Dark energy challenges our understanding of cosmic fate. Black holes defy our attempts to unify physics. The multiverse suggests that our reality may be one of countless others. The more we learn, the more we realize how much remains unknown. Technology pushes the boundaries of discovery, but there are limits. Telescopes like the James Webb Space Telescope have revolutionized our ability to peer into the depths of time and space, yet even they are bound by observational limits. No matter how advanced our instruments become, there will always be regions of the cosmos that remain beyond our reach, hidden behind cosmic horizons, governed by laws we do not yet understand. The debate between finite and infinite remains unresolved. Does the universe have an edge, or does it stretch infinitely? Is it a closed system with a definite boundary, or is it unbounded in ways we cannot comprehend? The debate between these possibilities reflects our deeper struggle to define the limits of existence itself. If infinity is real, then everything that can happen will happen somewhere. If the universe is finite, what lies beyond its edge? The multiverse and the simulation hypothesis challenge our perception of reality. If our universe is one of many, then the laws of physics we take for granted may not be universal. If we live in a simulation, then the very fabric of reality may be artificial, a construct designed by forces beyond our comprehension. These ideas, once considered speculative, are now serious topics of scientific discussion. They force us to question not just the cosmos, but the nature of perception, consciousness, and existence itself. Curiosity is the engine of progress, and the journey is as important as the destination. The greatest lesson from our exploration of the universe is that the pursuit of knowledge is never ending. Whether or not we ever find an ultimate answer, the act of searching, of questioning, of striving to understand is what defines us. The process itself is what makes us human. Final thoughts on the infinite possibilities of space. The universe is vast beyond comprehension, stretching across distances so immense that our entire solar system is nothing more than a speck in the cosmic ocean. And yet, within this vastness, we exist small, fragile, and fleeting, yet capable of questioning the very structure of reality itself. This paradox is what makes our journey so profound. The fact that we, mere collections of stardust, can look out into the cosmos and attempt to understand it is nothing short of extraordinary. If we accept that mystery will always remain, then the universe ceases to be a problem to be solved and becomes an invitation to explore. The vastness of space is not something to be feared, but something to be embraced. It is a reminder that there is always more to learn, always another horizon to reach, always another layer of reality waiting to be uncovered. Some may ask, will we ever reach the final answer? Will we ever fully understand where the universe came from, how it works, and what its ultimate fate will be? Perhaps, perhaps not. But that is not the point. The point is that we are searching, that we are driven by an insatiable curiosity, that we continue to push forward, despite knowing that the answers may never be complete. And in that pursuit, we find meaning. Whether the universe is infinite or finite, whether we are alone or one of countless civilizations, whether reality itself is fundamental or an illusion, these questions define our existence. And as long as we continue to ask them, as long as we continue to reach for understanding, the universe will never truly be beyond our grasp. So, should the mystery remain open-ended? Yes. Because as long as there are mysteries to solve, the adventure never ends.